Hey everyone, welcome into lecture number 15 of Calculus 3. This lecture is on surface area. So let's start by just sketching a little picture to see what we're doing, and then we're just going to do a few examples in this lecture of computing surface areas of surfaces. So the surfaces that we are going to study are going to be, at least for this section, are going to be surfaces that are given by the graphs of a function. So here's our assumption here, but let's let z, I'll write it this way, let's let z equal f of xy be a function, so a function of two variables, of course, but a function defined over a plane region D, so maybe over more, but at least over this plane region D, such that its first partial derivatives are continuous. So with continuous first partial derivatives on D. All right, so that means that the partial derivatives exist, right? So the function is smooth in that sense. So these are going to be df by dx and df by dy, and they not only do the derivatives exist, but they're continuous on this region D. All right, so then what that means is that we have, of course, some. I'll draw a couple sketches here, but we have a couple things going on. Number one, we've got our plane region D down here, right? So there's our D, that's our domain of our function, x and y. And then the z, obviously, the function f gives us some surface here over D, right? And so in the past, what we've done is we've computed the volume of the surface sitting above this, this region, right? So this right here we would call gamma of f. This I wrote z, but it's really f, right? But this is our surface S. This time what we want to do is we want to talk about the surface area of the surface. So can we compute the surface area of this surface? Obviously, what we're going to do is we're going to come downstairs here and we're going to compute some kind of an integral over the region D, but we need to make sure that the integrand that we compute is actually giving us the surface area up here of the surface itself. So that's going to be the function. So rather than the height function, we want to measure the surface area of this surface. So what we'll do, as usual, is zoom in on a tiny little rectangle down below. We'll go up. That's going to give us a tiny little piece of the surface up here. And we're going to zoom in on this, okay? So we'll zoom in just on this piece of the surface. So I'm going to draw this piece of the surface like as follows. All right, so maybe, I'm just, making up this picture, but there's our piece of the surface. So this is our surface S. We want to know what's the surface area of this, right? So I'm going to call that ds. So this is going to be our surface area element. Element here just means tiny little piece of surface area, just like this picture represents over here. And then you can imagine you integrate these up, right? You take the limit, Riemann sum. It's a regular double integral over D. It's all going to make perfect sense, right? But surface area element. So this is what we want to know. What's the surface area of this piece? Now, what we're going to do is we're going to use the partial derivatives of our function to approximate this. And how are we going to do that? Well, instead of measuring the area of the surface itself, of this curved surface, that's kind of the point, is it's difficult to measure the area of this curved surface, right? What we're going to do is we're going to approximate this surface by its partial derivatives, okay? By its tangent plane. Its tangent plane at, say, this point here, this left end point. So let's say we're working at this point, which corresponds to this point over here on the surface. So it sits right above, say, that point, right? So this point P here. So we're going to approximate the surface by its tangent plane at this point, a tiny piece of its tangent plane. And the tangent plane, as we know, is spanned by the partial derivative vectors, right? And so that's where the partial derivatives are going to come in. So in this direction, this partial derivative is going to be the one that corresponds to this. So that's going to be our df by dy, right? This direction down here. And then the other partial derivative is going to be, say, this one, right? And so that one's going to be the one that corresponds down below to, I did it in red, but that's okay. So to this direction, right? And so that's going to be our df by dx. And so then once we have this, then we can extend and we can make a tiny little parallelogram here, tiny little parallelogram that we can use to approximate. We can find the area of this parallelogram pretty easily, actually. And we can use the area of that to approximate the area of the surface. And then again, in a limit, as these get really small, the area of the tangent plane, this parallelogram portion of the tangent plane, will approach the area of the surface itself in the limit, and therefore in the integral, right? So the exercise here that I'm going to leave for you guys is to work out, and this is in the book and it's in your homework in different exercises in the homework, but the exercise here is to work out the formula for the area of this parallelogram in terms of the area down below of the element down here, the area of the rectangle that it comes from. And it turns out, and it's pretty straightforward actually, so that's why I'm leaving it as an exercise. It's very similar to the derivation of arc length that you've done in Calc 2, but it turns out that this is going to be, so that the surface area element is going to be the square root of the sums of 1 plus df by dx quantity squared plus df by dy quantity squared at this point P, right, times dA. All right, so that is the surface area element. Please take a moment to work this out. You can review the derivation of arc length from Calculus 2, and this is going to be very, very similar here, right? So very, very similar. The formula looks almost the same, honestly, because the derivation works out exactly the same way. You just have an extra dimension to consider. Okay, so if we believe this formula, then what does that mean? Well, that means then that the area of this portion of the surface over this region D is just the integral, the double integral over D of that surface area element, right? So then the area of this portion of the surface over D, so I didn't write D in this notation, but it's going to be double integral of ds, and then we'll get D in here, right? This turns out to be the double integral over D of this integrand, so the surface area integrand. 1 plus dx df squared, I'll use this notation, plus dy df dy squared times dA. And so this is the integral that we need to work out. All right, so for the rest of this lecture, I just want to do 3 examples. Again, this is pretty straightforward. It's just a formula. We're just going to plug in and compute some integrals. All right, so let's try an example now. So as for our first example, let's try to find the surface area of the portion of a paraboloid. And I'll give you a formula here. So this is going to be the portion of the paraboloid z equals 1 minus x squared minus y squared. And I just want to know the portion of the paraboloid, the surface area of the portion that lies above the plane, z equals -2. Okay, so what I would recommend is first you have to, you just have to plug into this formula, right? So you have to find first what's f, then what is d, and then compute the integral. So find f, you can go in either order, I guess, but determine which one of these is going to give us the function f, which one is going to, how we're going to determine the domain d, and then from there you can just work it out. So I'll give you a moment to pause the video and work on that, and when you come back, we'll do it together. All right, now that you've had a chance to work on it, let's see how you did. So this is a paraboloid that opens downward, so I'm just going to sketch it. The sketch is not necessarily, but it's not required, I should say, but it might help. So this is a paraboloid that opens downward. We can tell that from the minus signs in both directions. So it looks something like this. It's got a maximum height of 1 in the z direction, right? So as we're going this way, this maximum height is 1, and then the plane z equals -2 is going to cut it, say, down here somewhere, right? And so then there's going to be an intersection with this plane down here, and so the portion that we want to find the surface area of is just this, right? And so this is the surface here, S, that we want to compute the surface area of. That is definitely going to be given by this function, right? And the domain is going to be, it's going to correspond to, say, this portion of this plane right here, right? So this, it's going to be moved up to the x to the xy plane somehow, in geometrically. But that's going to be the domain that we want to compute this over. So that right there, we need to figure out that formula. All right, so let's do it. Again, first of all, our f is 1 minus x squared minus y squared. We can compute our derivatives. df dx is going to be minus 2x. df dy is going to be minus 2y. And so we can compute our arc length element very straightforwardly, right? So our ds is going to be 1 plus 4x squared plus 4y squared times dA, all right? And then our region D, that is going to come from setting these two equal to each other, right? So we need to find the boundary here. So this is our setting our plane z equals -2 equal to our paraboloid, 1 minus x squared minus y squared. So when we set those equal, this is equal to z, right? So then when we set those equal, we'll end up with the following. So 1 minus x squared minus y squared equals -2. And just rearranging everything here, we get x squared plus y squared equals 3. So this is a circle on the plane of radius square root 3, right? So this is a circle with radius square root 3. And so that's the domain that or a disk, I should say, really, because it's the whole disk, right? But the boundary is the circle, and we're inside the circle. So that's how we get the disk. And so then our D is going to be, our region D is going to be the disk centered at the origin, right, with radius square root 3. All right, and so to compute this, we can probably switch this to polar coordinates, right? So we can make a change of variables and switch to polar coordinates. All right, let's write out the integral first, and then we'll make the change of variables to polar coordinates. So our integral is going to be double integral over this domain D of this function, 1 plus 4x squared plus 4y squared dA, right? And then switching to polar coordinates. So in polar coordinates, it's a good use of our polar coordinate studies, right? Our theta is, of course, going to go from 0 to 2 pi. It goes all the way around the circle. Our radius is just going to work out from 0 to root 3. So that's this is a polar rectangle. A circle is a polar rectangle, right? Which is a weird thing to say. And then remember that our dA has to become r dr d theta. The other thing then is how we're going to rewrite the integrand. Well, the integrand, 1 plus 4 parentheses x squared plus y squared square root, right? This becomes square root of 1 plus 4 r squared in polar coordinates. All right, so polar coordinates are going to be the best way to attack this one. And our surface area of this surface, right? The area of the surface is now going to be the integral from 0 to 2 pi, integral from 0 to root 3 of the integrand 1 plus 4r squared square root, then times r dr d theta. This is, of course, separable, right? So as it separates the theta portion of the integral, we've done examples of this, right? The theta portion of this integral is just going to give us 2 pi, and then the rest of this we probably should write out a couple steps, but it's also going to be pretty straightforward, right? So that's the integral in the r direction. We can make a u sub here, right? So if we let u equal 1 plus 4r squared, then our du is going to be equal to 8r dr. That means we need an 8 here and a 1/8 here, and then we can compute how our limits change. So u of root 3, this is going to be 1 plus 12, so that's going to be 13. And then u of 0 is just going to be 1. Okay? So this whole thing now becomes pi over 4, combining this, integral from 1 to 13 of square root u du. And that's it. All right, so as we compute that, so this then becomes pi over 4 times integral of square root u is 2/3 u to the 3/2 power. So that's evaluated from 1 to 13. Right, so this is then going to be, what, pi over 6, right? Times 13 to the 3/2 minus 1. All right, so another way to write this is pi over 6 times 13 root 13 minus 1. And we'll just leave it like that. All right, so that is the surface area of that portion of the paraboloid that lies above the plane. That's the exact surface area. All right, let's try one more similar ilk here, where you'll see what I mean. I'll write this down. But the next one, I would like to, instead of finding the portion of a paraboloid, let's try to find the portion of the surface area of a sphere. So I'll just write out the pieces here. Let's say we have the sphere x squared plus y squared plus z squared equals 4. And I want to know the surface area of the portion that lies above the plane z equals 1. So this is a sphere of radius 2, right? So I'm just going to sketch a sphere here. Right, and if this is the origin, the radius is 2, so the highest point here would be a 2. We want to cut this off by a plane, right? Cut this by the plane, z equals 1, and then find the surface area of this portion up here. So this is our surface right here. Okay, so once again, why don't we pause the video, take a moment, try to find the surface area of this cap of the sphere that we've cut off here. It's going to be very similar to the last one. So if you got stuck on the last one, try to work through in a similar ilk to what we just did, and I'll check in with you when you're done. All right, so let's see how you guys did. This one's, again, going to be very similar to the last one. What we'll have here, right, we need to solve for the function first. So the function is going to be solving for z. The z is positive in this scenario because it lies above z equal 1. So our function z can just be the square root of 4 minus parentheses x squared plus y squared. I'm preparing myself for the possibility and probability that we're going to be using polar coordinates here. I see circles, right? And then we also need to find our domain D, right? So this is our function z. Z equals f of xy. Now what we need to do is find the domain D. So the domain is going to be the intersection just like it was before. So we set these equal to each other, right? So z equals 1. We try to find the boundary, right? So when z equals 1, we plug it in and we see what happens, right? So to find D, we say x squared plus y squared plus 1 squared, plug this in, equals 4, right? And so this is going to be exactly the same as what we had before. X squared plus y squared equals 3. And so therefore, this is a disk, right? The domain D is a disk centered at the origin. So centered at the origin in the xy plane, right? And then it goes out to the maximum radius is square root of 3. So very similar. It's a different integrand, although it looks somewhat similar. It's the same domain D though, all right? Same domain D. So let's work this out then. So we know exactly how our domain D works because we just used it, right? So in this one, the radius is going to work out from 0 to root 3, and the theta is going to go around from 0 to 2 pi. Our integrand, z, is going to become square root 4 minus r squared, right? And then we need to work out the area element. That's going to be much different than what we had before. So we need then to find ds, right? Remember, ds is the square root 1 plus dz dx squared plus dz dy squared times dA, and then we'll know dA is going to be in polar coordinates, right? So we need to work this out first though, right? So dz dx and dz dy are going to be very similar to each other. So let's just work dz dx and then see if we can understand how it's going to change. But this is going to be a chain rule, right? So the first step is the derivative of the square root, which is the outside. So that's going to be 1 over 2 square roots, 4 minus x squared plus y squared, and then times the derivative of the inside, right? So that's going to give us a minus 2x, right? So I'm going to erase this 1, and then by the chain rule we get a minus 2x, all right? And then of course this cancels, this cancels. It's going to get squared anyway, so the minus isn't a big deal. But that's the derivative. Now, just by comparison and by noticing all the symmetry here, we see that dz by dy has to be negative 2y, sorry, negative y, cancel the 2's again, right? But negative y over square root of 4 minus x squared plus y squared. All right, and so now we plug these into our formula. So this is now going to be big square root, because we're squaring fractions here, but it's going to be 1 plus, square these up and add them up, right? Look what happens. We get x squared on the top over 4 minus x squared plus y squared. Square root squares away. Plus, in this case, it's going to be y squared over 4 minus x squared plus y squared. This is all under a square root. Don't forget the dA. Right, dA is involved here. And then it's all under the square root, but we have to add it up. Right, so these two have the same denominator. This one's going to have to get similar, right, denominator. So then we're going to end up with 4 minus x squared plus y squared plus x squared plus y squared over 4 minus x squared plus y squared. All right, times dA. I keep forgetting the dA. Don't forget the dA. So that's got to be there. And then these, of course, cancel. This is just going to be a 2 over this denominator, right? And so we end up with our surface area element is going to be 2 over the square root of 4 minus r squared times dA, which is, of course, 2r over square root 4 minus r squared dr d theta. That's what we have to integrate. And again, we have polar rectangle, aka a circle, right? So the integral itself is going to be pretty good to go here. So we're good. Let's see what we have now. Our area of this cap of our sphere is now going to be double integral. So the first one goes from 0 to 2 pi d theta. I know it's going to be separable, so I'll just separate it to start. Then 0 to root 3. In the r direction, this is the integrand, right? So 2r over square root 4 minus r squared dr. And this is what we have to compute. So this one's 2 pi, right? This one is going to be another u sub. So again, we make our u equal to 4 minus r squared. Our du is then minus 2r dr. Our bounds are going to flip this, though. So u of root 3 is going to be 1, and u of 0 is going to be 4. And so this whole thing can be written as the integral from 1 to 4 of, so this 2 is already there. The minus sign takes care of the flipping of the limits, right? And so then this just becomes u to the minus 1/2 du, and that's what we have to integrate, right? So we end up with then 2 pi times 2 square roots of u, right? Antiderivative of this, evaluated from u equals 1 to u equals 4. And so this leaves us with 4 pi times 2 minus 1, which is just 4 pi. Okay, so after all that work, that's what we've got. 4 pi for the surface area of the cap of the sphere that lies above the plane z equals 1, the sphere of radius 2. All right, so I hope you guys got that one. I got one more example for you guys to work through here. This is number 4, item number 4 in this lecture. So this time I'd like to find the area of the portion of the plane that lies in the first octant. So the plane's equation is 3x plus 2y plus z equals 6. And again, I want to know just the portion that lies in the first octant. There are many ways to do this, but let's do it using the methods that we've derived in this lecture or talked about in this lecture. All right, so we can sketch this, and then I'll give you guys a chance to work it out on your own. But the first octant is, of course, where it's the only one that's numbered, right, in three-dimensional space, but it's where all x, y, and z are positive. So we just need to figure out the intersection points, so you just zero these out one at a time. So when x is 2, this will cross, so there's 2. y is going to be equal to 3, so a little further, and then z is going to be equal to 6, right? And so obviously this is a triangle. This is a triangle, but what I'd like you to do is treat this triangle like a surface that is the graph of a function whose domain is this region right here. So there's our domain D. Think of it as a graph of a function that maps up to the triangular surface here, and then compute an integral, a double integral, to compute the actual surface area of this triangle, so the area of this triangle. All right, so take a moment, pause the video, work that one out, and then when you come back, we'll finish this lecture off. All right, let's see how you guys did. Once again, we kind of know how this is going to go now, right? This time we're not going to need polar coordinates, but we do need our function. Our function is going to be z equals 6 minus 3x minus 2y, and we can go right into finding our surface element, right? Surface area element here. So remember, ds is 1 plus dz by dx squared plus dz by dy squared dA. And this is just going to be a constant, right? Because it's linear. But this is going to be 1 plus. The x derivative is negative 3, quantity squared, plus the y derivative is negative 2, quantity squared, times dA. Right? And so this one's going to be square root of 1 plus 9 plus 4 dA, or the square root of 14. And then this can be dx dy, dy dx, whichever one works better for us. So that again is what we need to integrate. So that's a constant, right? That's going to be a constant. So before we go too much further here, let's think about what this is going to be now. So our area of this portion, this triangular portion of the plane, is going to be the double integral over the domain D of this surface element, right? Which we just worked out to be the double integral over D of a constant, square root 14, times dA. Let's leave it as dA and not even worry about this dx dy. So this is then the square root of 14 times the double integral over d of dA. This is just the area. This right here is the area of this triangle D, and that's a right triangle. That's a right triangle. So we don't even need to use calculus to do that one. You know, I said we should integrate it, so integrate it if you want. But really, the main thing here, though, is to get this in terms of the double integral, which we've done, and then we can use geometry to compute that one, right? That last area there. So this is going to be the square root of 14 times the area of this triangle, which is 1/2 times base times height, right? So times 2 times 3. And so this all works out to be 3 square roots of 14. All right, so that's our answer. And that's the area of the surface, the triangular surface that sits above this triangular domain in the base, in the xy plane, right, in the domain space. So that's how we compute our surface area with double integrals. Let's leave this one here, and I'll talk to you guys in the next one.